Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to be an introductory video into the concept of mechanical vibration. After watching this video, hopefully you will be able to recognize a system that will be undergoing a vibrational or what's sometimes called a harmonic motion, and hopefully you'll know how to write equations of motion that describe the system. So let me talk about what we're looking at here. Imagine we've got some sort of mass M here that's attached to a spring which is attached to this wall. Springs have what's called an equilibrium position, so we're going to assume in this example at the position shown this spring is relaxed. And what I'm going to do here is I've already put an axis in with plus x to the right that I'm going to use to track the location of the center of mass of this object. So some important variables here. This object has a certain mass m. This spring here has some spring constant associated with it, k. And the spring has an equilibrium position, which puts this object at this location when the spring is unstretched. I'm going to measure x now from the center of this object, right positive. Now also in this example we're going to assume this is a zero friction surface, because again this is just meant to be an introductory video into vibration and I want to remove that complication from this video. So imagine now that this object is displaced an amount to the left that I am going to call A, and it's released. So what's going to happen is this object is going to be pushed by this spring, and that it's going to accelerate to the right. It's going to end up over here somewhere. Now once it crosses this line here, a very important thing happens. I'm going to go ahead and do this here. This line right here, I'm going to use as a datum for the spring basically. Once this object crosses these green dashed dots, the spring is now going to be stretched and the force is going to reverse direction. And what's going to happen is this object will slow down, slow down, slow down, and then it'll turn around, start speeding up, speeding up, speeding up. And then once it crosses this line again, the force again reverses direction. So an important thing to realize is anytime this object is to the left of this green line, the force direction applied by the spring onto this object is to the right. Anytime this object is over here somewhere, the force is going to be to the left. So it's very important to realize that the force is varying in both magnitude and direction, and it's varying by Hooke's law. Hooke's law, remember, is force equals a constant times x for a spring. Now this gives the magnitude of that force. You'll notice that whenever this is to the right, my x value would be positive. However, the force is to the left. And whenever the object's over here, my x value would be negative, and hence the force is to the right. So what I'm going to do is use a minus sign here and write the force on that object as minus kx. This now will give me the correct force direction whether this object is over to the right or the left. Now as far as how to analyze it, there are two types of equations we can write for this system. One is a Newton's second law type of equation, and two is a work energy type of equation. So what I'm going to do is I'm going to write out both. Now you notice I've already drawn the picture. Here's a picture of the system at equilibrium. Here's a picture of the system at a time I'm going to call t equals 0. The conditions of the problem here at t equals 0 are the velocity is equal to 0 because it's released from rest, and x is equal to whatever this value is that I called a to the left. I'll go ahead and put minus a here. These are referred to as the initial conditions of the problem, which I'm going to call, right, this is picture 1 here, and here's my picture 2. Now this picture is meant to be kind of an arbitrary position where the object, it isn't at x equals a, it's not at x equals 0, it's at just some generic x value. At the instant shown, I'm going to go back and draw that a little better. There we go. At the instant shown, the spring would be applying a force to the right. And that force can be expressed with this term, minus kx. Now there's also an mg acting down and a normal force acting up, but they're not relevant for the horizontal motion. There's no friction in this example. If there were friction here, we would want the normal, no doubt. But in a zero friction example, we don't need to worry about those. So this force is representing the force exerted by the spring onto this object. you'll notice that x is some negative number, and this will actually work out as a positive force, meaning to the right. Now, as a little side note, I'd also like to talk a little bit about the energy of this object. At the instant shown here, it is moving, so it does have a kinetic energy, and that kinetic energy is equal to 1/2 mv squared. It also has a potential energy. The spring is still compressed in amount x, so this has a potential energy equal to 1/2 kx squared. The sum of the two gives the total energy of this object here at this position. All right, so deriving equations of motion for an oscillating system. You can do it either by Newton's second law or with methods of work energy. Let's talk about the Newton's second law part. Net force is equal to mass times acceleration for this system. The net force acting on this object is equal to this expression. So the left-hand side of Newton's second law is going to be minus kx equals ma. Now, how you write the acceleration depends on the type of problem. In a lot of problems in physics, the accelerations are constant, and then a very nice way to put this would be just a for acceleration. And because if you have constant acceleration, the acceleration is just a numerical value in the problem. But in this problem, the acceleration is not constant. Notice that the force varies in both magnitude and direction. So just putting a for the acceleration really is not good enough. So there's two other possible ways we can write that acceleration. First, we could write it as dv dt. Well, notice that if I put dv dt here, I have a correct equation, but one thing to take note of is it has three variables, x, the v, and the t. So you can work it that way, but it's a three-variable problem, and there's quite a bit of math involved in solving it. The other way we can write that acceleration, right? Remember that the velocity is the derivative of position. So we can also write that acceleration as d squared x dt squared. And if you do that, we've got x as a variable, time as a variable, and this is x as a variable as well. So we end up with a two-variable equation. So this will be the preferred method here for what we want to put for that acceleration term, d squared x dt squared. This is referred to as the equation of motion for the system. It's a second-order differential equation, second order because it's got a second derivative here. I'm going to go ahead and put it in standard form and then talk about how to use energy to derive the equation of motion for the system. Standard form in most differential equation examples, you write highest derivative first with a 1 in front of it. So I'm going to take this guy and I'm going to write it first, and to get a 1 in front of it I would have to divide by the mass. So this equation written in standard form is going to look like d squared x dt squared plus k over m times x equals 0. And all I've done here is basically put this over on the right, divided everything by m, rearranged it slightly. So this is what's called our equation of motion for the system. Out of this will come a function that'll give us position against time that will describe the time-dependent position of this object. It'll tell us where it's at for any time as time moves on. I think what I'll be doing is probably making a separate video on solving it, because I see this one's pushing 9 minutes already. So we talk about, at least in this video, the second way to get the equation of motion for the system. All right, so I'm going to take this and just shrink it down a little bit. All right. Number 2, second way to derive the equation of motion for the system. And I'm looking at this position right here, my picture 2. This object presumably is moving to the right, but it doesn't actually have to be. Picture 2 could be after it's done something like this and it's on its way back to the left. So the velocity is actually good in either direction at position 2. The total energy of this system here in my second picture is equal to the sum of the potential and kinetic energies. So that's going to equal 1/2 kx squared for the potential energy stored in the spring plus 1/2 mv squared for the kinetic energy of the object. You will notice that this equation is good anywhere. It doesn't matter if x is positive or negative. This term ends up positive either way. Same thing with the kinetic energy. Now, This is the net force acting on the system, and that force is taken into account with this potential energy term. So the total energy of this system is constant because there's no external non-conservative forces doing work on the system. That means this is not changing, which means its time derivative is 0. So if we differentiate this equation with respect to time derivative of the whole thing here, the dE dt term would be 0. Because the energy is not changing. Now, if we had some sort of force here, like a frictional force or another external force acting on the system, this time derivative would not be 0. But in this example, we don't. This guy's time derivative is going to be kx dx dt. Remember that you have to chain rule this. So when you differentiate this term, you bring down the 2, subtract 1 times x to the first power. But again, x is time dependent, so it's got a time derivative. This term's time derivative, so we got to bring down the 2. That's going to be an mv to the first times dv dt. Because again, the velocity also is time dependent, so it's got a time derivative associated with it. Now, as we look at this equation here, here's some things to take note. dx dt is the velocity, so these actually can be divided out. And dv dt, remember, is equal to the second derivative of x with respect to time. So there's our equation as we clean it up a little bit here. And you notice it's basically the same as this. Putting it in standard form, you would divide by the mass. So we'd end up with d squared x dt squared plus k over m times x equals 0. You notice the same as we got before. So you can derive the equation of motion for a system either directly by Newton's second law or by methods of work energy. One thing about the Newton's second law approach, you have to make sure your equation used for the force is good on either side. You got to make sure direction is taken into account. That's why I've got the minus sign here. If you use energy, you write out an equation for the total energy of the system, and then you hit it with a time derivative. And in either case, you should end up with an equation in this form. Now, sometimes what will happen is, especially if you're looking at problems that have angles involved, you'll have sines and cosines over here, and you have to use what are called small angle approximations. And I'm going to save those for other videos here. So this is just meant to be an introductory video. And the purpose here is mainly to talk about how to derive the equations of motion. Hopefully that's been made clear for you. I'll make another one for how to solve them. Have a great day.